Okay, so without much ado, let me just introduce Huzur Saran. He's a professor at IIT Delhi in the Computer Science Department. I had the pleasure of working with Huzur about 15 years ago in conjunction with one of the early MIMO, WiMAX type of startup companies called IOSpan. We did work there together, and more recently we cooperated on some India-US type of research, joint research initiative. So it's a pleasure to have him here, and you have his bio for more details of what they're working on. Okay, well,
thank you. Thanks, Ray, and it's great to be here. I've heard about WINLABs often, and I've been involved, and Deepankar has been telling me many things about it, so it's great to be able to come here today. So I'll talk about, well, so as you know, there's this effort to do 5G, which is a way, it's a marketing term in the end, 4G, 5G, these are all initiatives done to try to say what's the next generation going to be. And what 5G is going to be and how shape it will take, I think over the next few years you will find out. But at least what people envision 5G to be, and I'm sure many of you are already familiar with it, but just to be on the same page, I'll do a couple of slides on that, and then talk a little bit about what we have been doing on device-to-device networking, which is one of the possible things that we feel are novel that can be done, right? And ours is not so much in the physical layer. We are computer science people, so we do more at the protocol layer and other MAC layer and above. So with that, and this is work done jointly with Vinay Ribeiro, who's also at IIT Delhi, and Huzur Saran, who's an architecture person at IIT Delhi. And this was partly supported by an Intel research grant we had. So, as I said, we will briefly talk about 5G and what are the issues in 5G. There is the whole issue of how much you always need more spectrum. You always have that argument. And then, of course, the near term is to sit on the common ground, so grab Wi-Fi and offload onto that all your traffic, and that's what operators all want to do. And again, I'm sure if it's too familiar to you, I can skip over some of these because I'm sure many of these ideas. And then the other thing people talk about a lot in Wi-Fi is, and there is some interesting recent results from NYU, for example, on millimeter waves and how millimeter waves can be a key differentiator for 5G, for achieving the targets. And again, we will briefly talk about what kind of targets they talk about. And then we will spend some time on our work on device-to-device sharing, where we feel that if you have a bunch of devices, like even in this room now we are sitting, and I think at least I see 12 laptops, and I'm sure in each of our pockets there is a phone of some sort, right? And then of course people have smart watches and smart footwear now. I was seeing earlier one of the research projects which was a smart thing on your foot to be able to detect if you're about to, while you're texting and you're walking, so you don't bounce against something, right? So that's a piece of research you have done here at WINLAB, I saw. So there is this business that we are going to have lots of devices all over the place, which there's an energy question how much they want to chat with each other, but they can chat with each other. And the reality is that today, most of the time what's happening is, even I have 2-3 devices, I'm getting first a notification, I got mail on this phone, then this notification pops up here, and all of these pop up and they independently download from the server a copy of the attachment, right? That's the most trivial case of it, but I'm just chatting with somebody, people are texting themselves even in the same classroom, person A is texting person B on WhatsApp or Facebook or whatever is their favorite application, and it's the way the applications are designed, it goes back to the server and then comes back, and of course it loads up your Wi-Fi net, wireless network, right? Whereas a lot of these things could be done at a device-to-device level itself. So these are one kind of things that we feel there is a potential for, and then beyond just sending messages to each other, maybe there is a reason you want to share the network connection for some reason, for diversity if nothing else. So I want to talk about that, and then we've also looked at some effort on offloading computation from a small handheld device to a laptop or a desktop that happens to be around in that same device-to-device context. So coming back to the big story, of course, there is this chart which I'm sure everybody knows by heart, that there was 1G, then there was 2G, then there was so many other Gs. And if you just recall, the big thing with 1G was the fact that you introduced spatial reuse. You introduced the whole notion of cells, right? And big thing with 2G was the whole going digital from analog and time division multiplexing. Later, of course, CDMA also came along. And also, first time you had some data services, at least SMS came along with 2G, or in a sense, right? That was the first time you started bringing data into the picture. And 3G was, and Edge was supposed to be higher data rates, 3D was supposed to be much higher data rates. And then we had WiMAX, which Paul, Ray and I both worked on one of those early companies, where we moved to much higher data rates, and then it was a complete packet-based backhaul, right? And of course, MIMO came into the picture, and with MIMO, OFDM also made sense, so we had another switch over in modulation technologies. And now people talk about 4G and carrier aggregation, TDD and FDD all thrown together. So this is old stuff, and I'm sure you're familiar with what all are the key features of LTE, so I'll skip this, right? So the question is, why do you want to go beyond 4G? And actually it's an important question, because yes, there is always more is better mentality in the computer industry, but where is it really, really needed? So if you look at it, there are two kinds of scenarios where the problem is today. Suburban / rural areas where because of coverage there's a problem. It's not that the aggregate data rate, the point is you just have towers which are very far away and you're not able to cover users. Often you find your cell phone keeps signing off, right? Even with the latest and greatest cell phones. And then there is this very dense urban settings, lots of people in offices, lots of people in malls, or other crowded areas, lots of people sitting in a stadium. And there the operators have a very tough time meeting the data expectations of most of the users, because the users still want to be able to watch the replay on their cell phone because they were eating popcorn while the actual game went on, right? So that's some of the reasons, and of course in the context of India, the number of users has suddenly gone up. In the last 15 years, we used to have 30 million landlines. And today we have 1 billion cell phone users. So the numbers have multiplied enormously. Most of those users still are, voice is their primary application, but data is beginning to become an application. And then in the context of India, with very, very high density of population, many of these problems get even worse. Right? So there is a reason for all of us to care to have extremely dense, high capacity networks, and also be able to cover the non so dense areas with adequate or good quality network. So that's what 5G is expected to do. And then of course there's the other aspect, which is this whole business of smart devices, sensors, like sensors that are supposed to live 10 years on a single battery, and then how do you connect that to the backhaul network and still not cause that? If you put an LTE modem into a sensor like that, it will not last more than a day, right? So because the protocol is so chatty, the processing is so high, so that is also an objective in 5G. So obviously now we know that, so as I said, to have high data density, you want small cell sizes. That's one extreme. And to have coverage, you would ideally like very large cell sizes, and that's where one of the conflicts is. And so you really have to do a mix and match there of different technologies. And of course, as you know, the ITU has started this effort, driven by the Europeans primarily, to define something called IMT 2020, which is going to be formally 5G. And they are talking about user data rates, that is, an individual user getting a gigabit per second. Right? That's, as I said, the desired objectives. We will see what is achievable and what the trade-offs are for doing 1 gigabit, whether the battery lifetime is adequate, whether we can do it or not. Right? And you want also anytime, anywhere coverage, connectivity, so you want enhanced coverage, high spectrum efficiency. You want it to work on even high-speed trains. So we, as was pointed out, right now we are trying to reach for all the possible things that right now 4G is not able to do. And that is the objective defined for us. Of course, the multiple efforts will need to be made in all these different directions. As I said, low power devices, and then there may be even need for supporting device-to-device communications effectively. Now, when we talk about 5G, there is the big things that people talk about that will happen, but there are a lot of stuff that is evolutionary in nature, which anyways in the pipe. You know, people are already enhancing LTE, voice over LTE. Then they are talking about making the network backhaul all supports of SDN, software-defined networking, and do cloud RAN. So many enhancements which are evolutionary in nature, which may actually happen with 4G or 4G plus networks without changing the air interface in a substantial way, are already in the pipe, and there are a lot of research going on around that. Device to device also, a lot of the things can be done without having to change the air interface, right? And then similarly there is this business of spectrum, combining dynamically trading spectrum between operators, things that many of you are, I'm sure, aware of. And then finally there is the stuff about using new spectrum beyond 6 gigahertz, whether it is 28 gigahertz or 60 gigahertz or 73 gigahertz. These are the commonly talked about bands, but I'm sure it's not limited to that. And the precise band is of some relevance, but the question is, how do you work in this kind of millimeter level, this thing? As we know, millimeter waves, of course, the one product that is available is the Y-Gig stuff, 1180, where you can actually do wireless HDMI, right? And that's 10 meter kind of ranges. And the question is, can you do better than that? And that's where there is a view, and there's work that has done, initial work that Tom Rappaport and a number of groups have done, which shows that you can actually do, if you use the many antennas that you can pump into a single, like this size device, you can have 16 antennas, and then you can do much more aggressive MIMO, even line of sight, and do a lot better.
Excuse me?
Yeah.
Is the claim there that there's 16 antennas on that?
Yes.
5 millimeter?
Yes.
5 millimeter?
I don't think, yeah, this is 5 millimeter and there are 16 antennas. That is the claim. And this is straight from this paper from Ted Rappaport at NYU. So
I see a little sine wave on the bottom of the chip. I thought maybe that was indicating the size of a wavelength there.
Could be,
yeah.
Yeah. Yeah. So yeah, and that's what they claim. In fact, this Samsung has something where they say, actually you don't need any area on your phone. What you can do is in your phone, at the edges of your, at the bottom and top edges of your PCB, just little bit, you can put 10 antennas here, 10 antennas here, just at the edges without actually consuming any area of the PCB itself, just by having this little patch antennas at the edges. And Samsung has built something like that. So that is the claim, that you can have a couple of dozen antennas on the phone and many more on the base station. And their argument is, they say that yes, as you go in towards the higher band, your propagation distance drops because the path loss drops. But by having so many more antennas, I can get MIMO gain. And their maths shows that the MIMO gain can more than compensate for the path loss exponent drop, and under certain assumptions and under certain experimental conditions, they have showed 200-meter distances with these kinds of millimeter wave devices, right? So that's what is driving the interest in. And of course, the key benefit is if you're doing at 28 gigahertz or 63 gigahertz, then it's very easy even with to get tens of gigabits or 20 or 30 gigabits of capacity in a single cell. See, that's the plus side of it, that with all of that thrown in, the capacity can potentially be much, much larger. Right? And that is what is driving it, that in urban settings, where if every user wants to have 1 gigabit and 30 users are there in an office the size of WINLAB, then each of them could be getting a gigabit. You need 30 gigabits of capacity, so with a few base stations you could do it. But the flip side is the following. See, with millimeter waves, even our human body becomes a shield, it doesn't go through properly. So if I'm standing like this, and I'm standing like this, and the APU happens to be here, this phone can't listen to me. But if the AP is there, it can listen to me. So I may need to have multiple APs even in a single room for this to really work, because coverage is very poor with a single AP. You will, even in a room kind of setting with number of humans present, you may only cover 30% of the people with 30% of the area with line of sight, another 30% with non-line of sight, and there will be another 30 to 40% of the area, if it's a single AP somewhere, where your signal will just not reach. Even despite the reflections and all that, you will not be able to get the processing done to get through. So that is where the challenge is. So what they want to do is, you'll have to put multiple of these devices. But if you can make them cheap enough, just like Wi-Fi access points, that may still be a viable option. And related to that, maybe I should bring that up here itself. Related to that is the whole idea of making your cell what is called edgeless. I'm not sure how many of you are familiar with this idea, but so let me just go over that. So the idea of an edgeless cell is that normally you have a cell, and if you look at this picture, I've drawn the traditional three-sector cells, and then if you look at a node here or a node here, these guys are edge of cell users. They are not really getting a good signal from any of the cells, right? And this is a key problem today, where that most of us, our house often happens to be an edge of cell for some reason, right? You're doing a call and you keep getting dropped off, right? And this happened to me even yesterday. So it's despite the latest and greatest phone and everything. So what the idea here is, and this is of course an old idea, that if the transmitters and receivers at the three nodes here were to cooperate with each other, so that they cooperatively sent the signal, parts of the signal out to me, and when I sent back a packet, each of them cooperatively received, they each got some reception, and then they combined the reception, right? So that's about you needing to do, after all, there's a path from here to here, there's a path from here to here, there's a path from here to here. And this may get you 1/10 the energy that the direct path, but there is still enough energy on each of these three paths, that if you were to combine the reception of these three paths and do a proper signal analysis of that, then you could actually pick up and get a much higher data rate down as well as a much higher data rate up. Of course, for this to work, and this is what is called coordinated multipoint, and this is actually a LT study item for the next release. They want to put it in early. The advantage of this would be, of course, great, that even the person here, sure, he is not at the edge of each of the three cells, but since now he can talk to all three of them, he still is able to get a high performance. Because the network works hard, these three guys coordinate with each other, and that is where the problem is, that from an implementation problem viewpoint, in some millisecond time periods, what has to happen is, first, whatever the transmission from here, which is picked up by these two guys, for example, has to be sent over to this base station in less than a millisecond, so that the base station can then combine the three signals do the computation, decipher what was transmitted, and send the packet off. Because the other objective is that you don't want to increase end-to-end latency, and you want end-to-end latency in the few millisecond range, ideally in a 1 millisecond range for control kind of applications. Right? So that's the challenge of implementing it, but again, this is something people are, physically people are comfortable that they can do. And in a building kind of setting anyway, all the wireless access points have Cat5 cable going to a controller. So it does not seem extremely difficult to make this happen. The basic infrastructure is already there. So that's one idea of putting in massive MIMO, using cooperative multipoint and sorry, let me just so the second thing that's happening, of course, is more near term and which can be done today, which is densify the net, make the cells smaller, and once you make the cells smaller, you also talk about having multiple carrier aggregation, as in 2 carriers and you're operating on both carriers. That is, of course, something that is already available. But now people are saying, okay, one of those could be Wi-Fi. So you have one primary carrier, which is proper LTE, and there's one which is Wi-Fi. And that is, there is this whole idea of LTE assisted access, which goes on, or you want to just offload to Wi-Fi, which is now quite popular in the US already, as you are all aware. And these are all ways by which you can sort of get new spectrum for free. If you are an operator, then what you're doing is you're saying, okay, there's all this free spectrum, which we don't have to pay for, and which we can leverage to increase our capacity. And if most people offload in their offices to Wi-Fi, then the radio resources become available to service the users who are outside offices, which is a small fraction of the total number of users, offices and homes and malls. Right? So this idea of Wi-Fi offload is very attractive, and in some sense it is already happening. The challenge is often in the building what you have, the two aspects. One, whether you will get a good quality of the voice call if it is just going over the internet here, right, is one question, right? Because you are not directly connected to the backhaul, right? You may be going through your office's ISP and then other things. So ideally you would like that there was a peering arrangement where a large office or a large mall already had a connection with the operator, and the operator had one, so that all your traffic just went on that. So those kinds of issues are there, but it is otherwise there is not so much of many of parts of this approach has already been adopted in many parts of the, including in the US and many other countries, and in fact even Indian operators are beginning to try it, but the challenges of adoption and there are still some challenges about how secure these communications will be. Over Wi-Fi, if the network is not so secure, will your calls get intercepted? Right? All those kinds of concerns also become relevant. Because you typically, for example, when you sign on to on a mall or a hotel, you sign on to the network, it is by default not encrypted. See, it's an open network, you sign on, and then you give your ID and something. But the basic wireless connection is unencrypted. So somebody can sniff that. And then if you're doing a voice call on top of it or other traffic on top of it. In an office normally you use WPA2 or something, so then it is encrypted. But in malls, in hotels, in other public places, the default setting is not encrypted. So those kinds of issues, security, privacy issues, are there which need to be thought about. Okay, now let's, and then, so as I said, that was about many of the things in 5G that people are doing work on, and some of our colleagues are also working on some of these things. None of us are right now working on millimeter waves, but on the other aspects we have some individual projects going on at IIT Delhi. Now let me talk a little bit in the next 20 odd minutes on the kind of work we have been doing on D2D networks. So as I said, the idea is you have a bunch of devices in a neighborhood, and of course somehow you have to work out that these devices have some relationship of trust, and that can depend on the context. So if it's your own devices, you could pre-configure them with some key or something. If it's an opportunistic thing like a meeting and you want to share, then there may be somebody who has to approve a connection for it, right? So that part depends a little bit on the context, but once these devices can talk to each other and form some kind of a network, they can even relay packet among the network. What is the value of that? What can you do with that? So that's the thing we are trying to explore. So the kind of things that come up is, suppose one option is you are in a home and you don't have too much of a good internet connection on any one device. Can one device share the other devices share the internet connection on one device, right? Or more generally, this device as well as this device has internet connectivity. Can both of them offer this as sharing, and I can decide which is the better connection and use that? Now one may ask, well, what's the big deal? I can just set this up as a Wi-Fi hotspot, and then all these devices can use it, right? Yes, that's a basic thing, so it's available today. Some of the catches with that is, once you set a device, your phone up as a Wi-Fi hotspot, you have no control on how much each of these guys is using it. For example, this happened to me only recently, that I had a new Windows laptop and I was working on it, and then I had stepped out of the home, so I set up my phone as a hotspot and I continued to work on it. And then a half an hour later I just looked and suddenly I got a message, my plans monthly budget is over. Because what had happened is the Wi-Fi, the Windows laptop had decided to download and update automatically over the connection. See, that's the problem. Once you say I shared the hotspot, I can't really say in the default way that things are set up, that okay, I'm sharing the hotspot, but each device is given a budget. Or no device is supposed to hog the connection. There are 4 of these devices using it. There is some limits on how much they are able to do, and some fairness guarantees I give them. So, and related to that, you can say, okay, this guy has 2 gigabytes of data available, and this guy has 4 gigabytes of data available. So I may want that these devices are told how much they can use, and one device is told you can go this way, whereas another device is told you can go this way, and then it actively monitors the consumption and adjusts for that. So when I talk about internet sharing in a device-to-device context, what I am trying to say is that that's what my intended application should give me, the ability to A, control how much I share, there's an upper limit, set a budget, whatever it is. B, be able to have simultaneous connection, something big is to be downloaded, maybe I should be able to download it simultaneously on both these connections. Right. So these are some of the things that I talk about when I talk about internet sharing. In terms of the details of how this network gets set up, so what we have done, we have implemented this using Wi-Fi Direct as a starting point, and rather than having a manual process in a traditional Wi-Fi hotspot, you have to have a manual process. You actually set up a hotspot, and then each device you load the password for that hotspot. That's what you have to do, right? Whereas here with Wi-Fi Direct, the only manual process right now is the allowing of a new connection on the person who starts this whole process, but not, that is because you do want to retain who all agrees to, who all you include in your device-to-device network for security reasons. But after that, there is no manual process. So as I said, and why have we used Wi-Fi? Because Wi-Fi is the device-to-device. You could actually use Bluetooth also if you wanted to. That would work fine too. Except that Bluetooth has lower data rates, and we felt that with Wi-Fi Direct you could just have the higher data rates and have something that would work across all sorts of devices. And this is so with that, what we were able to do is make a multi-hop wireless network. But our focus was, again, you see, in a traditional ad hoc network, you can have lots of hops. And we felt that lots of hops has its own problems. Routing becomes very messy. Stability of the network is also, as you know, because if people are leaving and joining the network, stability is an issue. Formation of such a network, maintaining it, the larger the number of nodes in it, and the more the number of hops, the bigger the challenge with that. So we felt that most of the value for the kind of application we are looking for would be achieved by at most having a small number of hops. In this particular case, we have chosen to pick maximum of 2 hops as our limit. So that's how we have designed it, that we do not want a very large network, because then you also lose performance, because every time a packet gets relayed through 2 or 3 hops, the capacity of the overall network goes down a lot. With that, we built some, students had fun, they tried to build different applications. Some are obvious and fairly trivial. One is just a simple chat application that works over the D2D network, right? There's nothing very complex to that, but it's just a nice, interesting application. People in the same room can talk to each other without having to go back to without even having necessarily a cloud connection. As I mentioned, internet sharing. So we've developed our internet sharing thing, which actually which has many of the features I've talked about. One of the issues there is also, and that I wanted to highlight, is when you're saying that we are going to have a D2D network and internet is going to be shared, and let's say 2 or 3 devices are there in that D2D network, which are capable of sharing the internet, and so they are offered to share the internet. Now I have, as a client, to decide which one I send my communication to. For that, I need to be able to find out which of these connections is faster right now, or what is the state of each of those connections. How good is it? Is it a high capacity, medium capacity? Is it data rate very low? Is it what's going through this connection or going through this connection? And also, within the D2D network, how good am I? My connection to you may not be very good, whereas my connection to this other device may be much better. So I need to do both the QoS sort of estimation of the current network state or network QoS state, both of the backhaul link and of the link within the D2D network. And so we had done some work on that. Again, I will not have
so
time.
So I have a question. So going back to the example you pointed out, where you were getting a notification simultaneously, like on my cell phone, I got the same notification, then I got it on the email. So how would that work here? So who would
So that, as I said, that one won't be, but internet sharing won't address that. That would need a separate application. So we have to, that's the problem. When you say D2D, maybe the applications have to also be intelligent enough to leverage that, right? And like email, if you have to actually go change email to work, that would need something of a change to the email client itself, right? Like for example, if you look at something like the file sharing app like Dropbox. So Dropbox has a feature where it recognizes that there is another device on the same LAN which is also got a copy of the data. So in that case, it does what is called Dropbox LAN sync rather than downloading from the network. So suppose this is happening with me, and I'm sure you must have seen it, that if you have your on your laptop or your desktop, you are already synced up on your Dropbox account. If you set up a new laptop on that which happens to be on the same LAN, then the syncing of all your 5-10 GB of data happens very rapidly because it does it locally. And that is an intelligence of the Dropbox app itself. Right? Whereas, and the problem is every app has to do it. Now the question is, can we do it at a network layer so that it gets abstracted? That may be difficult. Because, by default, most of the applications, like an email server, has an SMTP and IMAP gateway setup. It will only contact that. Now, I can play games with that and intercept that, but that may not be such a good idea anyway. Because you may mess up with your mail privacy stuff if you try to do that. So, yes, that was a motivating example. We have some examples where large data, if you want to share, you can do it. We have a couple of other apps that we build, some of our students build, that I'll just show you.
From a user's point of view, when you're doing that, you're talking about moving huge quantities of data around now, right, on these networks. How do you check the integrity of the data? You sync 10 gigabytes of Dropbox data between two laptops. How is that checked?
Yeah, okay, so fair enough. So, in the case of Dropbox, first of all, I don't do it, it is the Dropbox app. And in that case, the way Dropbox app works is, every file they divide into chunks. For each chunk they build a signature, right? And the server has a signature. And what you do is, every time you transfer a chunk, you verify the signature with the server.
After it's been received?
Yes, I believe so. Right? Again, the Dropbox is the protocol is secret. It's a proprietary implementation. There is no public documentation. So we don't know completely what they do inside. But that is basically what happens. Because there are other applications like OwnCloud, there are open source versions also. They all do the same thing.
So typically, how big are these chunks?
Few K, typically. 4K, 8K, 10K.
So essentially hashes.
Yeah, and then hash it, yeah.
So you hash all 10 gigabytes every time you
In
move
fact,
around.
most of these file sharing apps do it even internally. See, suppose I do the following. I take a common file and I copy it into my laptop. Or you give me a file. You give me a USB drive, I copy it into my Dropbox. Now, it could be that Dropbox already has a copy of that file synced up. In that case, what will happen is, when I stick it in, the local Dropbox app client will chunk up the file, build signatures for all of them, and send the signatures over. And at that side, they say, oh, we already have a chunk with this signature. You don't need to upload it at all. That's some of the ways they save on both on even storage capacity there. They will not, if 10 people make 10 copies of the same file, Dropbox in its storage server will, using sort of a dedupe technology as it is called, deduplication, will have one copy only of that, with appropriate indications saying that the other guys are pointing. So that's what happens. So coming back here, so we do some probing of the QoS, and all I wanted to remark is that often the traditional way on the wired internet people have done network pathcar and all of those tools is they send a bunch of packets with evenly spaced and then look at how the spacing spreads on the other side to estimate what the available capacity is. Now the catch is doing that kind of thing over LTE kind of networks is not such a great idea, because many of the wireless networks actually wait for what happens is they come to the base station or to the access point, and then they wait for a LTE slot, for a slot allocation, which may cause a delay, and these two packets which had a gap when sent will actually get coalesced into a same slot and sent out. So you will not be able to measure the spread the way you were expecting to. So what we found is when we did try to use those kinds of tools for doing some of our bandwidth estimation, that they did not really work well over a 3G or 4G connection. And what you had to do was slightly different kinds of tools, which were more trying to transfer a bit of data across and see what the performance you get, but don't end up doing a 1 gigabyte file or 1 megabyte file download just to estimate network capacity. That would be a waste. So how to do it with a very minimal amount of actual data transfer. And so we built some, I can skip most of this now. So as I said, based on some of the QoS things, our system will actually dynamically select which gateway to go out on. I already talked about it. So another kind of application that we built is a file system sharing application where I can share a bunch of files with anybody in my D2D network. Any file I store here, of course, the assumption here is that what I am sharing, the other people trust me, right? This is assuming, we are not saying you go to a stadium and everybody else becomes part of your D2D network, right? Only your friends become part of your D2D network, then you can work with this. If you start making untrusted outsiders part of your D2D network, then most of these things then even you will not want to share an internet connection on that D2D. So there is an underlying assumption that the D2D network is among parties, either they are all from the same family or a bunch of friends or in an office setting or in a school class group setting. There is some reason people are willing to share across that, or it is just my own devices, a whole bunch of them.
Target's shown how effective one can do that.
Yeah.
With friends and not let anybody else in.
What did you say?
Target, for
Yeah.
example, show how effectively they can keep their friends in and distinguish between vendors who are friendly and vendors who are not friendly, and other kinds of people.
He is being sarcastic. There's all
I'm sorry, I
kinds
was
of
being a bit sarcastic. It's extraordinarily difficult.
Target had this whole problem, right?
Because somebody can be a friend on one side and
Sure.
not so friendly on the other side, and
Or
relationships.
if the friend can actually probably the problem with Target was once you have so many friendly vendors, right? And one of the vendors doesn't have such good security, so he gets hacked.
I think I think it's more complicated than that, because the definition of a friend is really complicated,
Yeah.
right?
Yeah.
You're in a business relationship in
Yeah,
particular.
as a
where
friend,
you can-
acquaintance.
right. And, yeah. that-
But, I mean, there is something to it in proper context, like within your own house. If the technology assures that propagations are very, well, let's say you're only doing it over millimeter wave, so you have pretty high assurance that this thing is not going through the walls.
That's great. Teenagers
Right,
have
so-
never been known
so
to
that
do
context is
unreasonable
very-
things.
Well,
So as soon as you have a key into a large space without
Right.
layers of security, you've got a real problem.
Even within, among your own stuff, if you have an iPhone, if you have an Android terminal and a Windows computer, you're now as safe as the least secure of the three.
Yes, or the least secure of the combined interactions between the
Right.
three. They
So-
could both be secure, but their interactions could have holes in them.
right, but I think in the right context, if the type of if you can limit the type of interaction that you're doing, right, this kind of thing can work, but what you need technologies across all layers that say these types of interactions are going to be available when there's an appropriate security context that's associated with them, and then I have other technologies that say, whatever happens here is gonna stay within that boundaries, and can't compromise everything else that's going on. So I wouldn't just completely exclude
Oh,
it.
no, I'm just saying that it offers a real challenge,
Right.
because it's a new set of context.
Yes.
And we have a demonstrable inability to do that well.
No, I think that's a fair point, that definitely when you're trying to do this kind of sharing, that how to make sure security, privacy, those kinds of things are not compromised, or what is the policy framework under which you want to work. These all become things which need to be thought about and put into place. Otherwise you can run the risk of...
It's even more difficult now. It's interesting, you watch what's going on in the news. is if the failure rate is very low and low enough to be acceptable 20 years ago, it won't be acceptable now because it'll end up on the front page of a sharing site saying this doesn't work, even though the rate is actually very low. Right? It's hard to judge the real statistics. People are not good at judging those statistics.
Yeah, right.
One failure and everybody knows about it.
I agree completely that security is a very important consideration. So as I said, in terms of application, so then again another student worked on how you could build a file sharing, system sharing app where you could define a set of shareable files. You don't have to share your whole file system. And then everybody who defines that, you can again put in some keys and all that also to prevent, to limit access to this, right? Then those files become accessible to others and they can just get it from the other device without having to go through the back. Again,
If those files end up being executed, which most of them are, for example, the video files and so on, how do you keep Trojan horses out of them when you share only part of it because you're only partially happy with the people you're sharing with?
well, video files are not necessarily executable. If you are just having ABI or something, it's not
Right.
executable. So, or if it's a JPEG or movie or picture file, those are definitely shareable.
Wasn't there a JPEG flaw like a decade ago where just opening a JPEG file?
Everything has, every piece of software, somewhere or the other, some flaw has been discovered. It has been patched also, so supposedly it is now not there, but it may be, unknown ones may still exist. And that unfortunately is the challenge with all of the computer industry. So depending on how paranoid you are about security, you have to make a choice. But if you want to share something and in a certain context you want to copy a file over or just share it, then this becomes possible. Right? And again, you have to know what you're doing. In the end, that's buyer beware, as they say. You have to worry about that. But again, these are the details of it. I'll skip it. I think it's interesting. Now, one final thing I wanted to talk about, that is about that one thing we found is that when you talk about a D2D network, then actually using TCP to communicate is often not very, very effective. It doesn't give you the best performance. Why? See, actually, this is true even over Wi-Fi. And the issue is basically this, that if you're transferring a file over Wi-Fi, then every time TCP will send a packet, you'll expect a MAC. Right? And what happens is, so just to compare, what we did some measurements over a simple 802.11g network is that UDP performs almost 46% better than TCP on transferring just a large chunk of data. And the reason is the X. What happens is that normally in TCP you will send a 1500 byte packet and expect an ACK, and then send the next packet. That's the basic structure, right? And of course you can have congestion windows, you have a multiple bunch of packet sorts, ACKs are tracking. That's the more generic structure. But the catch is, to be able to send this ACK, and this is not the MAC level ACK that is built into Wi-Fi, this is the actual ACK data packet that is sent. What must happen is that this side of the NIC card here needs to be able to grab the channel. So you have to go through the whole Wi-Fi process of gaining access to the channel, write the preambles after that, and then send the packet. So the consequence becomes that, and you can look at this picture, this makes it much clearer. So you send a TCP data packet, and to send that packet there is a interframe spacing in the beginning, data interframe spacing. Then there is some preambles there is some other wait period, then you have a 20 microsecond preamble, then the actual data packet, and then this is the 802.11 level acknowledgement that is built into the MAC layer. But this is not used directly by TCP at all, unless you put in a lot of cross-layer features, which nobody does. What happens is, after you send this with 234 milliseconds of actual, microseconds of actual data and a whole bunch of overhead on top of it, now you're waiting for the other guy to send you back an ACK. The ACK, though it's a small packet, the actual amount of time you need to actually send just the bits of the ACK is 18 microseconds. But because of all the overhead, the whole ACK takes up 103 microseconds, which is a lot less than this. Right? So, though we say ACKs are actually small, so it should not be a problem. Here, it's a simple time division duplex channel, so the channel is not available for the downlink while the ACK is being sent on the uplink, and that itself significantly degrades the capacity. That was an observation we had. Of course.
So for instance, isn't this how my laptop works now?
No.
When I use Wi-Fi?
Yeah, so when you use Wi-Fi and you use TCP,
Yeah.
then all of this happens, which is why if you download a file over Wi-Fi, you're not getting the advertised data rate, you're getting less. Of course, anyway, because of coding and other things also getting less. Plus, you may be your signal strength and whatever it is using QPSK or what it is using will depend on what the signal strength is. So you don't worry about it. Only when you copy a 1 gigabyte file or something, then you bother about it. If it's a few tens of megabytes, you typically don't even bother about it, right? But that's why if you copy a file across from one laptop to the other large file, you'll typically see data rates of 1 to 2 megabytes per second, which is 16 megabits per second. Not even the 54 megabits of a 11G. And now most of our laptops are 11N, so which is supposedly going $100 beyond. Right? Of course, we accept the fact that most of this is advertising, this 100 is anyway an advertised number. So you will only get less. So nobody tries to investigate it. But we did some little bit of work on this. And we discovered this fact. And
But isn't it true that YouTube and Netflix all use TCP instead of UDP?
no, everybody does use TCP mostly. So, and for a wired network, this doesn't matter. Wired networks are typically all full duplex. So the uplink traffic doesn't interfere with the downlink. Right? All the wired stuff is like that. Even your Ethernet to your port to your desktop is full duplex. So this is not messing up anything on a traditional wired connection. It's only on the wireless connection that this starts to be a problem, and especially on short distance wireless connections where the RTT is small, right? Where you could push a lot more, and the loss rate is likely to be very low also. See, TCP would work well if loss rates are a little high, so you need to deal with all of the losses. So anyway, you will have to have overhead, you have to do it all. But if you're talking about a DTD, this laptop and that laptop talking, the loss rates will be significantly low.
Okay, so the short range is the thing.
That short range,
that's what I was
low
thinking.
RTT, right?
Got it.
Well, because TCP at the end of the day was designed to deal with
Congestion, right? It's looking for congestion.
and fairness.
It is designed for that.
Here, the only point of congestion is the AP, which has its own congestion management and fairness, and so you're putting something on top of it that's not.
Yeah, right.
necessary.
So it's not anything about TCP being negative about TCP, but it's just the interaction of what TCP is designed for and what it is getting used for in this particular context, right? Which causes some performance penalties. And one of the other issues with this is that now what you can do with this, one thing which is an old technique people have done is thin out the ACKs. Do an ACK per 2 packets, an ACK per 4 packets, which you can configure, and there is something called TCP delayed ACK, which people have talked about for doing this. The problem with that is that if you do TCP delayed ACK, then it also messes up with the whole process of TCP window expansion, slow start and this thing. Because now you will be getting only 1/3 of the number of ACKs. If you do it like 1 and 3 ACKs rather than this thing. So that, and as you know, TCP what it does is, in the beginning it will have one packet outstanding, it will send one packet. When an acknowledgement comes, it'll increase its window by the acknowledgement size, and suddenly it will send 2 packets. And then next time you will get, each of the acts will increase by another acknowledgement size, and in one RTT you should get 2 acts, so you should go up to 4. So you have this exponential increase of window size in the beginning, which is what we call the TCP slow start phase, and then later to avoid congestion you go into the slower linear increase phase. But this whole increase of the TCP window will get slowed down if you put in just TCP delayed acts blindly. Right? So you need to cut down the number of acts, but how to do it in a way that what should be a delayed act parameter? And you need to actually, and what this is the result of our work, is that you need to dynamically adjust the TCP delayed act parameter based on the network conditions. To keep it so the basic constraint you want to do is D should be less than CWA. So you should that at least one act comes every window, otherwise our timeouts will start happening. Right? Because you send its congestion window and then wait. And that will cause a timeout. So you definitely don't want to go to that level. So we need to estimate, and we don't know the TCP congestion window because that's a sender side parameter. And the delayed act parameter is a receiver side parameter, right? So we did some work on estimating the congestion window and trying to dynamically adjust D.
Presumably, you can infer the D right at the transmitter. If you start to observe that, you only see the even numbered acts,
okay,
right?
so
that you always go up by 2, and you're like, oh, right?
you could do that, but I'm just saying. What we are talking about here is changing TCP both at the sender and the receiver, which is typically not feasible. See, TCP at most what you can do is, if you are running a server, you can change it at your end. So that at the receiver your acts become less frequent, but you assume that whatever is the built-in TCP stack on the phone remains. That's one of the challenges with changing TCP, that it has to be backward compatible. And it has to be, you can't assume every device will have your version of it.
But I mean, if you're not so much talking about changing the TCP as re-parameterizing it.
Yes, but by default,
and with D2D, you have control over both ends, right? If you know that you're in the D2D mode.
No, but the kind of question that he said, that can the sender estimate the D parameter? So that would need a change of because by default that's not a standard feature. The sender doing an estimation of the D parameter, or the sender sending the congestion window to the receiver.
Right, but you can say on both ends, I'm in D2D mode, and therefore, as a sender, I use these parameters. As a receiver, I use these parameters.
Right, but as a sender, you can't fix CWND, for example. It's a dynamic parameter.
But you can count on the receiver to do it if you know that you're in D2D mode.
Then
and
the first thing
maybe
is
you discovered that you
I
guys
agree.
both
The
are
receiver
aware of this.
has to estimate what the congestion window is. Only then he has to increase his beat parameter when he knows that the congestion window has gone up. That's what I mean. Which is not too hard to do, but which can be easily estimated. Well, that's one of the things he did. And with all of that, these are some numbers. So if you look at it, if you have a fixed delay act parameter of 0, which means no delayed acts at all, you get 10 megabits on a certain communication. The same thing with delay act parameters of 2 or 4. So this is the case with a lossy environment on the right hand side. On the left hand is in a lossless environment. As you increase the delayed act parameter, you get increased throughput. Right? In this case, in a lossy environment, when you increase the delayed act parameter, actually things get worse because of the losses. Right? The R implementation, which dynamically adjusts D based on the CWND and this thing by estimation, actually is able to get a consistent win in both cases of about 30 to 40%.
Have you actually tried it over the air?
Yeah.
Or is it only non-straight? Well,
Oh yeah, right now it is an NS3. I think their students have already implemented it. I'm not sure whether the final results on the air are still available right now or not. See, part of the challenge again becomes that on the server we have a Linux server, we could do it, but we don't want to go root the phone and then mess with the Android kernel inside on this side, on the client side. On the phone side it gets a little messier to do this. One other thing we also showed, this is a concern, that on the other hand, if you have two connections, probably try to finish off in the next couple of minutes also. So in this kind of a setting, if you have multiple competing TCP connections, one which is a traditional TCP connection and another which is which uses delayed acts, then because of delayed acts, this guy's window expansion will be a little slower than this guy. So they will not get equal division of bandwidth. This guy, the traditional guy, will grab more of the bandwidth than the other. So this is one of the downsides, that in the competing setting, the traditional Neuron got 7.7 megabits, whereas the proximity implementation with delayed acts got only 6 megabits. So what we are working on right now is that let's just for D2D build a UDP based transport mechanism with whatever error control is there, we build at the UDP layer so that we just have a different protocol. And from an implementation perspective, it is simpler to do that rather than trying to change the TCP standardization. That's probably not even advisable. I will skip this thing. There's something called caching we can also do, where stuff that gets downloaded, we are able to cache that. And I already talked about this. I'll skip the details of this. This is more a module level implementation of the file sync system. I'll just spend 1 minute talking about the other piece of work we have done, which is about offloading computation from, let's say, my phone to my laptop. I try to do this where what you're saying is there's a phone here, there's a laptop here, they're part of a D2D network, let's say. Now I'm taking an image and doing something on it, building a panorama out of a video, for example. It's a computationally intensive task. Doing it on my cell phone, which is not computationally very strong, is not the most optimum solution. Ideally, if you could ship the video over to the laptop and then do the processing on the laptop and send the result back, you could do better. And we have some very preliminary results on that. I'll skip the details of it in the interest of time. Somebody wants to, we can always chat about it. Some of the challenges in doing something like this is, how do you figure out what parts of a piece of code gets shipped to the other side? What's your framework for that? And how to actually implement it? And also you have to worry about the fact, oh, I'm about to ship it to this guy, but what if the connection is not good between the two devices, right? So some of these things there has to be a dynamic decision on. But let me just get to the actual numbers. So for example, this is the number of the power consumption. When I did my shipping, so this is something very simple, just a matrix multiplication, large matrix multiplication. You do it on the phone. This is the kind of power it is using 89 milliwatts of power continuously during that fairly large computation. Whereas if you ship it, then in the beginning you use power because you are going to wirelessly transmit the matrix over, which will consume power. Then you wait for the result to come back, and then so the power consumption goes down. Right, so that's one reason to say, and we could show that if you did offloading, you actually conserve 42% of power.
Do I actually see that the time axis on the right
Is longer, which is probably not a good way of showing it. I'll just show you the actual amount of time it took, which is lesser. That's the more relevant thing. They've just taken a snapshot which is longer. See, the responses may have come around here, for example, or earlier, and this doesn't really show that. It's just showing a window of power consumption for a period. That's what they have shown. So in particular, what we did is rather than do matrix multiplication, which we have also done, but I wanted to just focus on one example here. Suppose you want to do just sharpening of an image using super resolution, which is a well-studied problem in image processing. So that algorithm you wanted to do. So you take this image, ship it over, and get the other guy to compute this sort of super resolved image out of it and send it back to you. So the kind of numbers we were able to get, this shows you an idea. So there are 3 bars here. The time it takes, after total time it takes, which includes the transmission time of the image, the processing at the other end, and the transmission of the result image back. That's the offloaded execution time. The time it takes to execute at the server, which is the computation at the server, which is this time here, the green bar, light green bar. And if it was to be run purely on the iPhone, then what is the time? So if you look at this, and this is shown for different sized images, so obviously the win becomes much bigger as the size of the problem becomes bigger. But you can see, for example, that what would take 70 seconds on the phone with a very large high resolution image can, even with the offload and communication part thrown in, be done in as little as 10 seconds with the offload. Okay, and again, this is something we are still working on, and